So as a part of maximum and minimum, we are continuously discussing different problems on optimization, problems on coordinate geometry, problems on plane mensuration, and today in this class we are going to solve problems on solid mensuration. Okay. See, I have a problem here, and the problem is about a sphere and cone. See, to solve these problems on solid mensuration as well problems on plane mensuration, we need to revise all known formulas from plane mensuration as well as from solid mensuration. Okay, you need to revise known formulas from these solid objects like cone, cube, cuboid, sphere, and then cylinder. Okay, right. You just, before going to solve this type of problems from your practice sheets, first of all you just revise those formulas. Okay, what is the volume of these solid objects, what is the surface area of these solid objects. You just make a list of all these formulas, revise them, and then try to solve the problems. And now look at the problem. A cone is circumscribing a sphere of radius r. A cone is circumscribing a sphere of radius r. Okay, if volume of the cone is minimum, then find its height. Okay, so actually first of all you just observe the problem, analyze the problem. I have a sphere. I think you all familiar with this sphere shape, right? I have a sphere. See, I need to inscribe this sphere in a cone. Okay, I need to inscribe this sphere in a cone. So how many cones are possible? You just imagine I have a sphere. That sphere is fixed. There is no chance to change the dimension of this sphere, but there is a chance to change the dimension of cone. You just consider many cones from smaller size to the larger size. Okay, try to inscribe this sphere in each and every cone. If you try that, there is a chance to inscribe this sphere in many cones, not only in one or two. There is a chance to inscribe this sphere in many cones, right? I have a sphere of some small size. I have cones of larger sizes. So there is a chance to inscribe this sphere in all those cones, right? But our question is, what is the minimum? What is the we need to find out a cone having minimum volume such that this sphere is inscribed in that cone. There are many possibilities, and among those possibilities, for one cone, the volume is minimum, and we need to find out that minimum volume. Maximum volume is infinite, because you just take a bigger cone and there is a chance to inscribe this sphere for sure in that cone. So automatically the volume is maximum volume is unknown actually. Okay, and so we need to find out minimum value. Okay, once again, what is the question? We need to inscribe a sphere in a cone. There are many possibilities for that cone. Among those infinite possibilities, we need to identify a possibility in which the volume of the cone is minimum and sphere is to be inscribed in this cone. Okay. See, coming to the required diagram. For suppose if you take a particular cone in which sphere is inscribed. For suppose I have a cone. If this is the cone in which sphere is inscribed. Okay. So we need to inscribe the sphere, right? Since we are searching for the minimum value, okay, since we are searching for the minimum value, if we inscribe a sphere in a cone having minimum value, for sure it touches the, this circular face of the cone. Okay, this is sphere and this is cone, and radius of this sphere is given as r. Since the radius of this sphere is given as r, this is r, and it's just like a circular shape, it touches, and this is also r. And when you join this vertex to the center of the sphere, we don't know this particular length, and if you consider height of the cone as some h, then this part will become like h minus r. Is it right? You just try to analyze the problem and you just imagine different variables related to the problem first, and then we need to solve. Okay. Right. And the next thing is, to solve the problem, I am just using semi-vertical angle of the cone. Okay. Take it as theta. Theta is the semi-vertical angle. this total angle is considered as vertical angle. For a cone, this angle is considered as vertical angle and half of that is considered as semi-vertical angle. Okay? Right. Okay. What is the formula for the volume of cone? Formula for the volume of the cone is 1/3 pi r square h, where this h is the base radius of the cone. Here it is, the base of the cone is also a circle and that base radius is the small r, whereas h is the height of the cone. Okay, so this is the volume and we need to maximize this. To maximize this, what we did? See, when you think about volume of the cone, which is 1/3 pi r square h, where this small r as well as small h both are unknown for us. Okay, so since we are going to optimize this volume of the cone, this v, so as we discussed in the previous problems, since we are trying to optimize this, we need to express this volume of the cone in terms of only one unknown value. But here there are two unknown values r and h. We need to eliminate any one of these two, and we need to express this volume in terms of single unknown, and then we do the usual maximum minimum process. So to eliminate one of these two, we need to get a relation between the small r and h from this what given diagram. Okay, so to establish relation between r and h, what I am going to do is, I just see this angle is also 90 degrees because just like circle and tangent, I just separate this smaller right angle triangle as well as this larger right angle triangle. For your convenience, I am just naming everything. Take it as A, take it as B, this as D, C, and then D as well E. Okay, you just pay attention on this triangle ABE. Okay, A, B, E. At B we have 90 degrees. Okay, at A we have theta. Opposite to the theta, this EB is radius of the sphere R, and AE opposite to 90 degrees we have it as H minus capital R. And now you just think about this total right angle triangle, and the total right angle triangle is A, D, C. Here we have 90 degrees and this angle is theta. This DC is the base radius of the cone, small r. AD is the height of the cone, H. Okay, and since this is H and this is R, we will write it like square root of R square plus H square. Yeah. Now when you compare these two triangles, theta and theta, same angle, 90 and 90 same. We have two right angle triangles. Either we may go with similar triangles or you may use any one of the trigonometric ratio. For suppose if you go with sin theta, what is sin theta from this figure? Opposite side by hypotenuse. What is sin theta from this triangle? Opposite side by hypotenuse. So if you use sin theta from these two, we will conclude that r divided by h minus r is equals to r divided by root of r square plus h square. Once again, we have a plan to solve this particular problem. We need to minimize this volume, but this volume is there in terms of two unknown variables, but we need to eliminate any one of these two. To eliminate any one of these two, we have to establish a relation between these unknown r and h with the known capital R, and this is that particular relation. To establish this relation, I am just taking this angle as theta and we are concentrating on these two right angle triangles. Okay. Excuse me. Alright, excuse me. Just have a look now. Yeah, how to eliminate any one of those variables. Yeah, for space I will erase these two. I am going to erase these two triangles and I will manipulate this. Okay. I need what? What we need to say? So you just have a look. We have this particular relation from these two triangles of the diagram. Since we are establishing relation between r, small r and small h along with the capital R. you just do squaring on both sides and then reciprocal on both sides. Okay, see, h minus r whole square by capital R whole square is equals to r square plus h square by r square. See, there is a chance to split it in such a way. And now send this one this side. This h square by r square is equals to simplification of this part, h minus r whole square minus r square divided by r square is this h square minus 2rh by r square. See, now you just make r square as subject. R square is equals to h square, r square by h square minus 2rh. It's completely algebraic calculation. Okay, yeah, I have r square. But as I mentioned you, the volume of the cone is 1/3 pi r square h. So we need to express volume in terms of one unknown quantity, and that's why volume is equals to pi by 3. You just separate it and replace this r square with this quantity. And when you observe this quantity, there is a chance to common out h and cancel out. So h r square by h minus 2r is r square into that h. So this is the volume of the cone. And now see, r square is also a constant, because in the problem itself it is given that there is a sphere of radius r, and so this r is a constant value. You just separate it. So volume is pi r square by 3 into h square by h minus 2r. This is volume, and our task is to minimize this volume. So to minimize this volume, what we need to do? We need to do its differentiation with respect to the unknown quantity h, and we need to equalize it to 0. The question is about finding height only. So if you find height, then there ends the problem. Okay, as a critical point, if you find height, there ends the problem. I am just erasing this formula for the space. Okay, and now I am trying to calculate derivative of this v with respect to h. dv by dh is equals to this pi r square by 3 is a constant part. Separate it, and we need to apply differentiation for this h square by h minus 2r, and we are familiar. Denominator h minus 2r into the derivative of numerator h square is 2h minus numerator h square into the derivative of denominator. See, derivative of denominator h, for h it is 1 because we are differentiating with respect to h, and for 2r it is constant, so 0 into 1 divided by h minus 2r whole square. You just have a look. This is derivative of that volume with respect to h. And since we are trying to minimize the volume, so for optimization and for maximum minima, okay, anything you need to write. Okay, for optimization we need to use derivative of that volume with respect to h is equals to 0. Okay, so you just pay attention. Okay, when you equalize this complete part to 0, pi r square by 3 just combines with 0, h minus 2r just cancels with 0. You left with this numerator only, and now you just try to simplify this numerator part. 2h into h is 2h square minus 2h into 2r is 4hr minus h square is equals to 0. And then 2h square minus h square is h square minus 4hr is equals to 0. We have two possibilities, h is equals to 0 or h is equals to 4r. If h is equals to 0, then height of the cone is 0, that in the sense no cone is possible. If h is equals to 4r, then in that case, see, the volume of the volume of the cone is minimum. We have two options actually, h is equals to 0 and h is equals to 4r. See, h is equals to 0 means no cone is possible in this case. At h is equals to 4r, cone is possible, and for sure at that position volume of the cone is minimum. Okay, if you wish to check whether it is minimum or not, there is a chance for us. Second derivative test. You just calculate second derivative of this volume, d square v by dh square. You just calculate d square v by dh square at h is equals to 4r. If you calculate this, you will get this particular value as greater than 0. It conveys that at h is equals to 4r, volume is minimum. But actually I am just avoiding this part, that part, no problem. Okay, see, we left with only one extreme position, h is equals to 4r. Since the question is about finding minimum volume of the cone, so for sure at h is equals to 4r we will get minimum volume. Okay, if you wish to check, you just find second derivative at h is equals to 4r, you will get it as positive quantity. Okay, so at the end you just try to analyze the problem. A cone is circumscribing a sphere of radius r. If the volume of the cone is minimum, then we need to find its height. So for suppose there is a If suppose if this is the cone of minimum value which is circumscribing the sphere, circumscribing in the sense cone is outside of the sphere, inscribing in the sense cone is inside of the sphere. So since the problem is about circumscribing, this is the position. Okay. Now see, when you mention volume of the cone as 1/3 pi r square h, where r is the base radius and height is the height of the cone, these two are unknown for us. So we need to mention volume of the cone in only one unknown value. So to eliminate any one of these two, we need to find a relation between these two in terms of the known constant. For that, I am just using this triangle AEB as with this triangle ADC. From there, we have this particular relation, and on simplification, we have r square in terms of h. R square is equals to h square by r square by h square minus 2rh. Use that r square in the formula of volume of the cone. Try to minimize it. So for that, calculate its derivative, equalize it to 0. At the end, you will get h is equals to 4r. Okay, have a look. That's the problem.